Hi everybody, welcome back to another episode of Science with Mr. Emond. Today we're going to be looking at the difference between heat and temperature, and we're going to need to talk about a few other things before we get into that. The first thing being kinetic molecular theory. So kinetic molecular theory is something that we would have learned about in 10th grade, and it basically states that all matter is made up of tiny particles that we call atoms. And those atoms are always in motion, right? Regardless of whether your atoms are in the solid state, liquid state, or gaseous state, they're in motion. And as you heat up an object, the particles are going to be moving faster. As that object loses heat, decreases temperature, those particles are going to begin to slow down until eventually it's possible that those particles stop moving completely. That would happen in the absence of all heat. That's absolute zero, completely frozen. And so this is kind of the main idea that we're going to be working with. And we're just going to do a little bit more review. So if you have something solid, like a solid crystal, think about the desk that you're sitting on right now, that solid wood or metal desk. Well, it has atoms that are linked together by very strong forces, very strong attractive forces. And even though they're bound very tightly together, they're still moving. They're vibrating, right? Back and forth. And they're staying in a fixed position. Liquids, though, have weaker forces. So the forces between the atoms are a little bit weaker, allowing them to move around, right? So they're able to move apart from one another and move around quickly, which is why you can see liquids flowing. Gases have the weakest forces between them. So they're going to be further spread out, moving about much faster than liquids, and liquids move much faster than solids, the atoms I'm talking about. And that's because of the strength of the bonds between them. Okay. When we're talking about heat, of course, we have to talk about the transfer of heat. And when we're talking about heat, we also interchange the word energy, right? So let's talk about conduction. If you have a metal rod, like this one here, and you apply heat to one end of it, like this, what will end up happening? Will I eventually feel this heat in my hand? Of course I will. The heat that's applied to one end of the rod, like in the picture here, these particles are going to absorb that energy. They're going to start getting really exciting, despite being like before they might have been vibrating like this. And after you applied heat to them, they're going to start moving quicker until they're just vibrating out of control. And when they're vibrating out of control, they're going to start bouncing into the atoms next to them. And when atoms collide like that, energy gets transferred from one atom to the next. And so you can see the chain reaction here. As atoms collide with one another, the heat is going to be transferred down the rod, and eventually it's going to touch my hand, which is here with 3 fingers apparently, and I'm going to feel that heat. And if the torch is hot enough, which that one definitely is not, but if it were a torch that produces a lot of heat, you would eventually feel that in your hand, and you would have to let go of that metal rod. That's convection. So it's transferred through a solid surface as those particles gain energy from the heat source, vibrating faster, colliding with one another, and the energy is transferred from particle to particle. Convection works a little bit differently, right? In Canada, our homes experience, the weather systems can be cold at some points in the year, and we need to heat our homes, and most of us have these in-floor, near-floor heating systems where we have vents or water heaters near the baseboards. And what these do is they release heat. So here I'm trying to draw some heat here being released. This heat from the warm air that's released from the vents is less dense than the air around it. And what happens is this hot air starts to rise. Okay? This hot air rises up because it's less dense. And as the warm air rises, the cool air near it, the cool air here, is going to move in to replace the vacuum that was left by the hot air rising. And this causes a net movement, a net flow of air. As this rises and gets away from its heat vent, that heat, remember, these gases are going to be bumping into one another. And when these gases bump into one another, energy is transferred. And that means as more collisions happen and energy keeps getting transferred, those particles are going to lose their energy because they're giving their heat to cooler particles. Heat is always going to move in the direction of something that is hot to something that is cooler. Not necessarily cold, but has less heat. It always moves in this direction. And this is a one-directional flow. So eventually our hot particles that originated near the vent start to cool off. And as they cool off and become more dense, they start to fall. And this creates a pattern, a current, a convection current. The last type of energy transfer that we're going to discuss today is radiation. And radiation is the transfer of energy by electromagnetic waves. Waves like, well, light waves, right? Which are like photons coming from the sun, right? So when we're talking about light energy coming from the sun, we can also think of them as photons of light that are carrying heat energy, heat radiation. And this is in the infrared portion of the electromagnetic spectrum. And the energy that's carried from the sun in these waves of photons, they travel through the vacuum of space at the speed of light, and they can travel through gases. And so they just travel from the sun to Earth, and energy is transferred in this form through radiation. Let's think about this picture here. What's happening? We have 3 ice cubes sitting on a solid surface, and they appear to be melting. So what's happening to the ice cubes? They're gaining heat from somewhere, right? They're gaining heat from somewhere, and that's causing them to melt and change state from a solid to a liquid. And we can see the liquid water starting to pool around them. Where do you think these ice cubes are gaining energy from? 2 things should be coming to mind here. They're sitting on a dark solid surface. We know that dark surfaces tend to absorb more energy, right? Especially when it comes to radiation energy, energy from the sun, from light waves. And that's because those waves are going to be absorbed by dark material and reflected by light material. And so this table or whatever countertop it's sitting on is going to be absorbing radiation energy, and then via conduction it's going to be transferring that energy into the ice cubes, causing them to melt. So there's 2 forces at play here causing these to melt. The first one, radiation energy, and the second one, conduction. Again, I want to start thinking about heat and temperature and how they're different now. So we have 2 beakers of water here. We have beaker number 1. Beaker number 1 looks like it has about 100 milliliters of water. Beaker number 2 looks like it has, what is that, maybe 220 milliliters of water? Let's say that I put in my thermometer, my temperature probe. I'm not going to do fancy drawings here. I put in my temperature probe, and they read out at exactly the same temperature. That temperature is 21 degrees Celsius, and that's because it's just sitting on my table in my room, and it's at room temperature. So we have 1 beaker with 100 milliliters of water at 21 degrees Celsius, and we have another beaker with 220 milliliters of water at 21 degrees Celsius. Here's my question to you. Do both beakers have the same amount of heat? We know that they're the same temperature. Do they have the same amount of heat? And the answer is no. They do not have the same amount of heat. even though these beakers, so here's my 200 milliliter beaker, and here's my 100 milliliter beaker, even though they're at the same temperature, they're room temperature, they have different amounts of heat content. And I want you to think about this for a second. If we started off with the beakers of water at 0 degrees, 1 degree Celsius, let's say one just above freezing point. They're at 1 degree Celsius, so very cold. You have them in the fridge. If they both started off at 1 degree Celsius, and this was 100 milliliters of water, and this was 200 milliliters of water, and you wanted to heat them up to room temperature, 21 degrees, you would put them on a conduction surface, right? Like a stovetop. If you did that, which one would take longer to heat up? Which one would you have to transfer more energy to? The 200 milliliters of water. There's more water, so it will require more energy to heat up to 21 degrees Celsius. Meaning that in the end, this 200 milliliter beaker of water has absorbed more heat, more energy, and thus has a higher heat content than this 100 milliliter beaker of water, despite starting off at the same temperature and finishing at the same temperature. Let's think about this example. Now we have the same amount of water, but they're at different temperatures. One's at 36.8 degrees Celsius and one's at 32.2 degrees Celsius. Do they have the same amount of heat? No. Why not? Well, we need to start talking about, now there's the same number of particles, right? Let's say we were doing stoichiometry. Let's say that there's 152, I should probably use my pencil. Let's say that there's 152.8 times 10 to the 23 H2O atoms in both beakers. Well, these ones are at a higher temperature than these ones, which means these particles in here, and remember there's the same amount in both beakers, the particles of water in here, in this one, they're moving faster because they have more heat. And we know they have more heat because they're at a higher temperature. These ones have less heat because they're at a lower temperature. And we can only do this comparison because they have the same number of particles. So let's start getting some definitions going on here. Thermal energy is the total sum of all the energies in a substance. If we look at these two, let's say the temperature is the same. They're 21 degrees Celsius. Here we have 1, 2, 3, 4, 5. We have 6 atoms of, let's say, carbon dioxide. And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 atoms of carbon dioxide. If they're at the same temperature and each atom is vibrating and has a heat signature, how much heat comparably do these two systems have? And you should be able to guess if they're the same temperature, then figure 2 is going to have twice as much thermal energy as figure 1. Why? It has twice as many particles that are vibrating due to their heat at the same rate. Let's define temperature. When you go outside and you might say, oh, today it's a pretty hot day. And yesterday was a hot day too. Does that mean they were the same temperature? Maybe. How would you prove it? Well, you have to measure something. When you take something's temperature, it's usually going to be measured in one of these three things: Celsius, Kelvin, or Fahrenheit. Now, if you're a Canadian, which one do you use? Celsius. If you're an American, which one do you use? Fahrenheit. Who uses Kelvin? Scientists, like you. scientists use Kelvin. Let's talk about the one we're probably most familiar with, Celsius. When you go outside and you measure the temperature and the temperature is 44 degrees Celsius, what would you say to me? Is that a hot day or a cold day? You'd say, that's a hot day, right? How hot? 44 degrees Celsius. What are you measuring there? Because when you give me a measurement, like 8 centimeters, we know is a measurement of like length or distance. Celsius is a measurement of the average energy of the particles. So when we go outside, if your thermometer is hanging in the air, what's happening is those air particles are hitting that thermometer, they're transferring energy to it, and when that happens, the thermometer is going to change its temperature until it matches the temperature outside. So, let's talk about heat. Heat is the thermal energy transferred from one object to another due to differences of temperature. Let's say that we have a burner. So here's my knob that controls the heat, and here's my burner, and it's plugged into a wall somewhere. So this hot plate is very hot, okay? And let's say we're applying, this is made out of, let's say, copper. This is a copper hot plate. And we're actually just gonna put a piece of copper on top of there. So these two metals, they're the same. If this piece of metal was at room temperature, and I turn on this burner onto, let's say it's 100 degrees Celsius, so this was 21 degrees Celsius, and this hot plate is 100, and I put this copper piece onto this burner. What's gonna happen? Well, we know that convection is gonna happen. There's gonna be a transfer of energy from the hot plate to the copper piece. And what's going to eventually happen? Well, this is going to heat up to 100 degrees Celsius, right? They're going to be the same. Would this be true if when let's say I heated up the hot plate to 100 degrees Celsius, and then I placed the copper particle on it, and I turn off the hot plate? What temperature would the copper piece get to? Would it get to 100 degrees Celsius this time? No, probably not. Because as heat is being transferred from the hot plate to this, the hot plate's now going to be losing its heat, right? So the hot plate might finish off somewhere like, I don't know, I'm just guessing now, somewhere around 80 degrees Celsius, and the piece of copper might finish at 80 degrees Celsius. Regardless, they're gonna finish at the same temperature. Why did I guess 80? It's because by my drawing, the hot plate is much larger than this, right? So it has much more heat content. So the temperature of the copper piece is probably going to increase more than the hot plate decreases. I'm just guessing, right? But we're getting into a little hint of what's about to come. And there's going to be a formula that we use for this, which we're not going to get into today. But if we're trying to figure out exactly how much heat went from my hot plate into the copper piece, if I'm trying to figure out how much heat, the symbol for heat is Q. How much heat was transferred into my copper piece to get it from 21 degrees to 81 or 80 degrees? How much heat did that take? Well, that's actually going to be a measurement of joules. And we're not going to go into the formula there, but the unit for heat is Q. And let's say it took 10,000 joules to increase the temperature from 21 to 80 degrees. The symbol for joules is J. Joules is a unit of heat whose symbol is Q. So we talked about that there's different scales. You have the Celsius scale. The Celsius scale is based on the properties of water. Water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius, right? And so we can use these as a measure of how hot or cold it is. If something's 0 degrees, well, outside, that's pretty cold, right? That's the temperature at which water freezes. So you're gonna start getting ice on the road, transition from rain to snow. That's kind of cold, right? If it's 50 degrees Celsius outside, that's pretty hot. That's not enough to boil water, but that's definitely enough for you to want to seek shelter and go inside where it's shaded or air conditioned. Something that's 100 degrees Celsius, you probably don't want to be dropped in a pot that's 100 degrees Celsius. That would not be pleasant. Remember these rules. As things cool off, they get smaller. As things heat up, they get bigger. In Canada, we have to worry about that, especially with things like tire pressure, right? When it gets colder, those gases are going to contract and we're going to lose volume in our tires. When it starts to heat up outside, the gases within the tires are going to expand and we're going to gain volume in our tires. And that's going to affect the pressure of your tires. And so in Canada, we want to keep checking the temperature of our tires because if it gets too low or too high, you can damage your tires. We know in science that we can reduce the temperature of something by removing heat from it. So let's say you have a beaker of water in an enclosed system and you want to take it from 0 degrees Celsius and you want to see how much heat you can remove. Can that water become negative 20? Of course it can. If you remove heat from it, you can turn the water into negative 20 degrees Celsius. Now it's going to be ice, right? Can you keep going? Yeah. You can have it at negative 100 degrees Celsius by removing more heat from it. How far can you go? The answer is negative 273.15 degrees Celsius. This is the lowest temperature that an object can reach. And think about what's happening. As you remove heat from an object, the particles within that object are going to be slowing down until eventually they stop moving. They're so slow, they're no longer moving. That happens at absolute zero. At absolute zero, there is no movement of particles in solids, liquids, or gases. There's no energy left in the system. It's the absolute zero. And this is going to lead us into the next temperature scale, the Kelvin temperature scale. And this is the temperature scale that scientists like to use. And it's based off absolute zero, which means it's a really good measurement of heat. If something has zero heat, there is no energy on that object, in the system. If it has zero energy, that's 0 degrees Kelvin. 0 degrees Kelvin, if we were talking about something in Celsius that has no energy, it would be negative 273.15. So these two things are equal. Now, the interesting thing that happens is that with the Celsius and the Kelvin scale, if you increase the heat of this system by 1 degrees Kelvin, you would do the same thing to the Celsius scale. They're equal. So 1 degree Celsius is 1 degree Kelvin. So if we increase from 0 Kelvin, absolute zero, to 1 Kelvin, which is still ridiculously cold, but now there's some energy and there's going to be just the tiniest bit of movement of those atoms. What temperature is that in Celsius? Well, that would be negative 272 2.15 degrees Celsius. So they both changed by 1. What would be at 100 degrees Celsius? Water boils. What would that be in Kelvin? Well, you would take 273.15 and add 100 to it. So 100 degrees Celsius would be 373.15 degrees Kelvin. And so now we're going to get into some conversions. To go from Celsius to Kelvin, you just use this formula here. You take your degrees Celsius and you add 273 to it. So if we're 25 degrees Celsius and you add 273 to it, what is 25 degrees Celsius in Kelvin? 298. If you're going the other way, let's say you have 393 degrees Kelvin and you want to know how many Celsius is it? Well, you subtract 273. So you take your kelvins, 393 kelvins, subtract 273 from it, and your temperature, 393 kelvins, is going to be the same as 120 degrees Celsius. Fahrenheit is the temperature scale our American friends like to use. The rationale behind this scale, I don't know. I don't know if there is a rationale. 0 degrees Kelvin is absolute 0 degrees Celsius is the freezing point of water. There's rationale between those. I don't know. I don't think 0 degrees Fahrenheit is anything. It's nothing. I don't know why this system exists. But you're going to be interacting with Americans, dealing with Americans, so you should know how to convert. Now, if it's 20 degrees Celsius in Canada and you're talking to an American and you're trying to explain to them whether that's hot or cold outside, this is the formula you use. So you take this 20 degrees and you multiply it by 9/5 and then you add 32 to it. And so 20 degrees Celsius is 68 degrees Fahrenheit. Now what I tend to do, because I don't carry a calculator around all the time, is I just use this rule. If it's 20 degrees outside, I'm going to multiply that by 2 first. So that's 40 degrees Fahrenheit. And then I'm going to add 32 to it. So that would be 72 degrees Fahrenheit. Now, is 20 degrees Fahrenheit 72 degrees? No. But it's pretty close, right? So you can do an estimation rather than multiplying by 9/5, multiply by 2, and you can get there pretty quick. Like if I was looking at 5 degrees Celsius, well, what is that? Multiply by that by 2, add 32. That's about 42 degrees Fahrenheit. Remember I said about 42 degrees Fahrenheit. So now I can have a conversation with an American and say, it's 5 degrees outside. That's like 42 degrees Fahrenheit. Does 42 degrees Fahrenheit mean anything to me? No, but it means something to them, right? What's meaningful to me is the 5 degrees Celsius. I know that that's pretty cold, but an American might be like, I don't know, is that cold? Is that hot? I have no idea. What it really is, remember you're doing 5 times 9/5 plus 32. So it's not 42 degrees Fahrenheit, it's actually 41. But you can see by estimating, we got pretty close. Like at least now we can have a conversation about it. Why don't you give these a shot? So do these conversions. We're not going to worry too much about Fahrenheit here. On the worksheet that you have for homework, there are some calculations for Fahrenheit just so you can get kind of good with it and have those conversations with our neighbors, our American friends. But we're not going to worry about it here in this video. Try these out. Pause the video here. Welcome back. Let's go through our answers. So to convert from Celsius to Kelvin, you're going to add 273. Okay? So here's your answers. 300 Kelvin, 833 Kelvin, 89 Kelvin, and 0 Kelvin. To convert from Kelvin to Celsius, you're going to subtract 273. Here's your answers: negative 163 Celsius, negative 251 Celsius, 129 Celsius, and 50 Celsius. That's it for today. That's our introduction to heat and temperature. See you next time. Thanks for watching, everybody. You can like, follow, and subscribe to my social medias to get notifications as soon as new content is uploaded. In the top corner here, you will find the playlist that this video is in. Watch the unit from beginning to end, and over here, you will find the next video in this unit. Keep learning, everybody. Take care.